Hi, this is Mr. Mack. We're going to be talking about um, a technique of integration called partial fractions, or we're going to be talking about integrating rational expressions by the use of partial fractions. So one of the best ways, I think, to start out would be to kind of show you what it is that we wish to do. Now, in this first problem here, we have the integral of x plus 1 over x squared plus x minus 6. Now, to do this problem, what we want to do is we want to split this fraction up into a sum of two fractions. Notice the denominator actually is x plus 3 times x minus 2. So the way we start out with this is we say, well, x plus 1 over x plus 3 times x minus 2 should be equal to some number a over x minus 2 plus some number b over x plus 3. And what we'll endeavor to do is to find the values of a and b to give us this numerator. Well, first of all, notice if we multiply by the quantity x plus 3, x minus 2, the left-hand side of this equation becomes x plus 1. Now the right-hand side becomes a times x plus 3 and plus b times x minus 2. Now, this equation has to be true for all x. Well, now, obviously, if you think about it, x can't be negative 3 or x can't be 2. When we have these values in the denominator, but they are removable singularities. So we can actually treat this equation as if it's true for all values to find out what a is. And there are some special values that are nice to use. For example, if we let x equal 2, then the equation becomes 3 is equal to 5a. And of course, b times 0 is 0. And so that implies that a is going to be 3/5. Now, another value that is easy to use is we can let x equal negative 3. Now, that gives us negative 2 is equal to a times 0 plus b times negative 5. And that gives us that b is equal to 2/5. Negative 2 over negative 5 is 2/5. So our original integral can actually be rewritten as the integral of 3/5 times 1 over x minus 2 dx plus 2/5 integral 1 over x plus 3 dx. Now, each one of these is pretty easy to do. This is 3/5 natural log of x minus 2 and plus 2/5 natural log of x plus 3. And of course, we do have the constant c. And there are things we can do. We can say that this is the natural log of the 5th root of x minus 2 cubed times x plus 3 squared plus c. Now, sometimes what we'll even do is we'll take this plus c and say it could actually be written as plus the natural log of k, for example. And so, by the properties of logs, this can become the natural log of k times the 5th root of x minus 2 cubed times x plus 3 squared. So what we do in this partial fraction problem is we take each of the factors and make it the denominator, and then in the numerator we come up with a numerator that is 1 degree less than our denominator. In other words, a is a number because our denominator is linear, our numerator is degree 0, and same thing with b. Now, if you have a problem like this one, the problem is a little different because X cubed plus x squared becomes x squared times x plus 1. So what we have is a repeated linear factor. Now what we do with something like that is we write 1 over x squared times x plus 1 is going to be equal to a over x plus b over x squared plus c over x plus 1. Since we have a repeated linear factor, we write fractions with each of those denominators up to the power of that linear factor that's repeated. But we don't increase the power of the numerators as we're doing that with repeated factors. So if we multiply through by x squared times x plus 1, we get 1 is equal to x times x plus 1 times a plus b times x plus 1 plus c times x squared. And once again, there are some values of x that will be very propitious for us to use here. If we let x equal 0, that gives us 1 equals 0 times a plus b plus c times 0. So 1 is equal to b. If we let x equal -1, that gives us 1 is equal to -1 times 0 times a plus 0 times b plus c times -1 squared, so that's c. So c is 1. And then we have run out of really propitious values of x, but we have values for b and c, so we can pick another value for x. Let's just let x equal 1. And what we're going to do now is we're going to plug in the 1 for b and 1 for c, and that gives us the equation 1 is equal to 1 times 2 times a, which is a, plus 1 times 2 plus 1 times 1 squared. Okay, and this gives us 1 is equal to 2a plus 3. So -2 is equal to 2a, which gives us a equals -1. Now what that allows us to do is to rewrite, we're going to have to minimize this a little bit so I have room here. Group this and shrink it down a little bit over here. So what this allows us to do is to rewrite this as the integral of 1 over x dx plus the integral of 1 over x squared dx plus the integral of 1 over x plus 1 dx. Now, I didn't do that quite right. One of these is a -1. Which one is it? It's the a, which is a negative. So the integral of -1 over x dx plus, and so on and so forth. Well, let's do this. We get negative natural log of x plus negative x to the -1 plus natural log of x plus 1 plus c. So this gives us the natural log of x plus 1 over x plus 1 over x plus c for the actual answer to this one. All right, now an example where we have a nonlinear denominator or nonlinear factor. Let's try the integral of 1 over x cubed plus x. Now 1 over x cubed plus x cubed plus x times x squared plus 1. And notice x squared plus 1 doesn't factor any farther, so what we're going to do is we're going to write 1 over x times x squared plus 1 is equal to a over x plus bx plus c over x squared plus 1. Notice, since this divisor here is quadratic, we made the numerator linear. Okay, well anyway, we'll just move this pointer out of the way. Now, multiplying through by x times x squared plus 1, we get 1 is equal to a times x squared plus 1 plus bx plus c times x. And so propitious values of x, I'm afraid there's only one this time. Let's let x equal 0. That gives us 1 equals a plus b times 1 plus c, b times 0 plus c times 0 is 0. So that gives us a equals 1. Now, we still need to know what b and c are. We don't have any more really wonderful values here. So let's try this. Let's let x equal 1. That would give us 1 is equal to a. Now we know a is 1 times 1 squared plus 1, that's 2, plus b times 1 plus c, that's b plus c times 1. And so we have negative 1 is equal to b plus c. Now let's try another value. How about x equals negative 1? That gives us 1 is equal to a, which is 1, times negative 1 squared plus 1, that's 2 still, plus b times negative 1, that's negative b, plus c times negative 1. So what do we got here? This negative 1 equals negative b, or positive b minus c. So now what we have is negative 1 equals b plus c, and negative 1 equals b minus c. So if we add these two equations together, we get 0 equals 2b, and so b is equal to 0, and then c, if b is equal to 0, is this right? Whoa, wait. Go back here, that's silly. We're adding this equation together with this one, that's going to give us negative 2 is equal to 2b, so b is equal to negative 1, and if b is equal to negative 1, in both equations we get c is equal to 0. Yeah, that makes sense. All right, so now, got a lot of minimizing to do here again. We have, what do we have? We have, this is equal to the integral of a, what was a? A was 1 over x dx plus the integral of b was negative 1. So negative x over x squared plus 1 dx. And then, of course, we'll finish this one up. This is the natural log of x. And we need let's see, we need actually a 2 here, so let's put a 2 there and negative 1/2 down here. So we get negative 1/2 natural log x squared plus 1 plus c. Now we can do this as the natural log of x over the square root of x squared plus 1 plus c, or we can make it natural log k here and put the k in front. So that basically is what we're doing. Now, anytime you have an integral where the degree of the numerator is greater than or equal to the degree of the denominator, what we do is we divide the denominator into the numerator and then integrate, and your fractional remainder of your polynomial division problem will be a fraction where the numerator degree is less than the denominator degree. So that is a pretty complete rendition of what we do with integration by parts. And we're done.